Welcome back. So in this video, we're going to actually check the conditions and write out the theoretical test for our test of two independent means. And we'll do the confidence intervals as well. So we're in lesson 12 here doing this situation with two groups of kids, 4-year-old children, watching 9 minutes. 20 of them watched a fast-paced cartoon, 20 of them watched a slower-paced educational program. Okay, and also this is kind of relevant to the condition, so I just want to refresh my memory on this one. The children selected for the study had no differences in attention or amount of TV usually watched. So that's going to have to do with our independence condition. So let's write those out. Okay, so let me see what else we've got here. It says use the estimated degrees of freedom and see how it compares to the calculated degrees of freedom. And the calculated degrees of freedom is 28.44. So see how that'll be given to you in a problem. And also notice it's not a whole number. So that nasty formula with the square roots in it gives you a decimal, and that's okay. They will accept a decimal input. The technology will. So then construct. So we're going to do our theoretical test at the 5% significance level. Then we're going to construct the equivalent confidence interval for the true mean difference between the two groups. Then we're going to summarize all of our results. We'll write our conclusion and check both of these using the Staplet theoretical calculator. Okay, great. So we got a lot of stuff to do. We've got a whole page and a half a page on the next page to do this. So let's do our conditions first. Independence. Okay, so the kids in each group and between groups must be independent in terms of wait time. Wait time for a treat. Okay, so can you see why they set up the experiment like they did? So they didn't just pick completely random kids. They also considered, they did some kind of interview. Whoops, got a typo there. They considered attention span, like previous or just sort of already from kids' lifestyle and constitution or whatever, what their, how did they word it? Their attention span and just the amount of TV they usually watch. Okay, so they did consider that. So consider attention span amount of TV usually watched. And there could be other factors, right? Like maybe we would want to consider socioeconomic level, urban versus rural, gender, right? Boys and girls kind of mature at different rates, right? So could that be a factor as well? So we want to consider all those things. Okay. Independence, randomization. Okay, the kids, and it probably says if they were randomly assigned, but they do need to be, yes, it says 60 kids were randomly assigned to one of the 3 groups, and we're just doing 2 groups. So the kids were randomly assigned to the groups. Okay, so that's great. Large population. Okay, so here's where we need to consider, is this one population or two? And I would say these kids are all coming out of a single population of, I'm going to assume it's US, so US 4-year-olds. The population of US 4-year-olds must be at least, and it's the size of each group, which might seem funny, at least 200, okay? Okay, last one, sample size. So N1 and N2 are equal to 20. So I don't know that this population would be normally distributed, because you can have an attention span, or sorry, not attention span, you can have a wait time of 0. And often when you're bumping up against a value like 0, that's going to skew the data, because you might have more towards 0, and then you have more room on the right to spread out, for the data to spread out. So I do have doubts about the population being normal. So let's check the sample about nearly normal. Let us, that is apostrophe, right? Let's check the samples for nearly normal. And because they're not over 30, that was the third option. Okay, so let's check that out. We already have, hopefully you still have it, we already have our data in Staplet here. We were doing this simulation in the first video. So now I want to go back and select histogram under the graph distributions. Okay, so this is pretty cool. And then you can also, is there a place to do box plots? Okay, it looks like we have to do the box plots separately. So I can compare the two box plots. Interesting. What do you notice? There's an outlier in the fast-paced cartoon group. So let's look at the two box plots for a minute. So the fast-paced cartoon group is definitely shifted towards a smaller wait time, right? And there's less variation, although this goes out to here. But there's an outlier of someone who, the kid waited it out for almost a minute, right? 47 seconds. So that can happen. And then in the educational program group, there was just a lot more spread, right? The IQR is way bigger than the IQR, the width of this box. So that's why we don't want to assume equal variances, right? We don't want to assume equal standard deviation. So here you can see the standard deviations. One is 10, one is 20. So definitely not equal. So we're not doing the pooled t-test, so that's good. And same mean and same means, yeah, that we had before. So it is interesting. So for two graphs here, we have to compare the box plots side by side and the histogram side by side. What do you think about nearly normal? What would you say? The fast-paced cartoon group, that looks nearly normal to me, but the educational program group is super interesting. This is like bimodal or trimodal, and it's really U-shaped. So you've got a big group, 5 kids, with a really small wait time, but then you've got a bunch in the middle, and then you've got another group, 8 kids, with a really large or long wait time. So I don't know about nearly normal on this. I don't think that's necessarily the case. It's not super skewed, but it's also not normal, right? It's symmetric, but not normal. And we've got this outlier. So I'm going to write down, I have my doubts about nearly normal, But I do want to continue this just to show you how we do the calculations, okay? So, but this would be interesting if we got this data. What would we do? There are likely other methods if you don't get, for small sample sizes, if you don't get nearly normal, they just go beyond the scope of this class. Okay, so I'm going to write a star here. There's an outlier in the cartoon group. And the educational program group is multimodal and U-shaped. Okay, so I have my doubts about nearly normal. I'm going to say not. Okay, not nearly normal. All right, so that's a bummer. However, we're this far, so I do want to do this. I'm going to write for practice. Okay, we do need to see how to use these formulas. Okay, let's write down our null and alternate again. Our null was mu sub cartoon group. Okay, yeah, just wanted to make sure. Sometimes I switch the order just to show you what happens. I'm going to keep the order. And also, yeah, it's good to practice confidence interval interpretations with negatives, so that'll allow us to do that. Mu sub cartoon minus mu sub educational E is equal to 0, so the alternate is they are not equal. Mu sub C minus mu sub E not equal 0, and I'll put my seconds on both of those. Okay, so there's our hypotheses. Let's do our T calculation over here. T, and we'll, degrees of freedom, we'll put that in to our T distribution. So that is the, let me get my formula here. Right, the sample difference that we already have, x bar 1 minus x bar 2 minus the null, which is 0, divided by the combined standard error. Okay, so we had 19.7 minus 33.85, or we could write the subtracted value we already know, minus 0. You can write that or not, it's up to you, over this big square root. And this is where we need the S values. So I'm going to go back to Staplet and go down to my summary statistics here, okay? So we have 10.6825. I'm going to write these down and then I'll show you. In the square root, 10.68, I am going to cut these down to 3. 10.683, because there's a lot to fit in there, squared over 20 plus 20.714 squared over 20. Okay, so here's our combined standard error here. So we have 10.683 squared over 20, you could put parentheses there or not, plus 20.714 squared over 20. Okay, so let's get a value for that. Or actually I want to make that higher. And I'll just do approximately equal or equal. Okay, so I'm going to use a Desmos calculator for this so I can see if I need to do any proofreading. And I have a subtraction, so I'm going to start with a parenthesis, or I could just put one, an ending one. 19.7 minus 33.85, close parenthesis, divide, oops, I guess I didn't close my parenthesis, close parenthesis, divide by, and now I'm going to have a giant square root, right? And I think this will work with order operations. If I go 10.683 squared divided by 20. Now I have to use the right arrow to get out of the denominator, and then plus. And then 20.714 squared divided by 20 as well. Okay, so a little bit of things with order of operations there and getting out of the denominator. Okay, so I'm getting negative 2.7151. Okay, put that in the notes here. Negative 2.7151, okay? So definitely getting up to 3 standard errors away. So let's find our p-value though. And if we're going to use the estimated degrees of freedom, that would be 20 minus 1, or 19, since they're both the same. The smaller minus 1. Let's find our p-value for that. So estimated p-value, and it's going to be 2 times, because it's a 2-tail. Let's go over to our t-distribution. We're going to put this into our t-distribution, and this is negative, right? So we're going to go to the left. Where's my t? We want degrees of freedom 19. We want to go to the left of negative 2.7151. Okay, I'm getting 0.0069. Okay, and also you could also do outside if you want to do, instead of multiplying by 2. 0.0069, so let's see what that is. I'll just go over to Desmos. 2 times 0.0069, 0.0138. Okay, here's the notes again. So p-value is 2 times 0.0069, which is 0.0138. Okay, so that is less than, oh, I'm so short on space here. This is less than 0.05. I barely got that on there. Now I want to do the calculated one just to see how that compares. So I'm going to switch to a different color. Calculated degrees of freedom is, they gave it to us in the problem wording, 28.44. So you can see it's higher than the conservative one. So how does that change our answer? So whoops, wrong place. Here's my t-distribution. So I would just change this to 28, change the degrees of freedom at the top to 28.44, replot. Luckily it remembers the number I had. And the area is 0056, so a little bit less. Okay, so I would say this one is more accurate, the other one is more conservative. Okay, so let me write my p-value. Is 2 times 0.0056. So I wrote that down, 2 times 0.0056. Let's figure out what that is. Zero, or sorry, 0112, which is also less than 0.05. Okay, so 2 times 0.0056, 0.0112. So this one is a little smaller, and that one's a little bigger, right? So the bigger would be conservative, right? Because you might bump up against the significance level and fail to reject. Okay, so that is the hypothesis test. I'll write out all the conclusion once we get done. I want to do the confidence interval first. And we got to remember, what confidence level are we going to choose? So I'm going to go back over on the left here. Confidence level for a two-tail. We're doing a two-tail of 0.05, so that is going to leave 95 in the center, right? So this is the 0.025, 0.025, or 1 minus 0.05 is 0.95. Okay, so we're going to do 95%. And we'll do this one both ways as well. We'll do both degrees of freedom and see how that comes out. Okay, so let's look at our formula for that. We have our difference between the samples, plus or minus our t star, and that's where we need the degrees of freedom. And then we have our standard error right there, okay? Which works. You can combine them if the variables are independent. So I'm going to put my difference here, 19.7 minus 33.85 plus or minus. I need that t star before I do the square root. So let's do df equals 19. It's a bummer because I got to put it back to 19, but also we're switching to value, right? Because the t star is a value. And central 0.95. Okay, to get the middle 95%, we need to go out 2.093 standard errors. Okay, so I wrote that on the notes. 2.093 times this big square root. Same one we had right up above there. So the 10.683 squared over 20 plus 20.714 squared over 20. Another nice thing about Desmos is you could copy from, you've got that in your formula, you could copy that part of Desmos if you wanted to. Okay, let's go to Desmos. Okay, actually you could copy a lot of parts, right? You could copy the top over as well. 19.7 minus 33.85. Oh, sorry, I keep doing that. I want to do this margin of error first. I just want to start with the 2.093 times the square root of 10.683 squared divided by 20, and then I got an arrow over plus 20.714 squared divided by 20. And also one tip, if you have a number pad on your keyboard, you can do your operations like plus and divide without having to do the shift key. I guess divide you don't, but plus and minus you have to do the shift key. So if that's helpful. Okay, so here's the margin of error. This is the plus or minus seconds, right? So we're talking about 10.9 seconds, so almost 11 seconds. So let me write this down. We actually need to do our difference. We need to do our difference here as well. So I remember that was negative 14.15 when we did it before, plus or minus 10.9077. And in our interpretation, we'll likely cut that down, but I just want to keep the 4 for now. Okay, and these are seconds. Okay. So now we can do our subtract and add. Negative 14.15 minus 10.9077 and negative 14.15 plus 10.9077. Okay, great. So negative 25.0577 comma negative 3.2423. Okay, so I probably did keep this negative, that way we get practice in interpreting confidence interval that comes out with 2 negatives. Okay, also seconds. Okay, so that was with the degrees of freedom equals 19. Let's do degrees of freedom equals 28.44 and see how that looks. Now for that, I don't really need to write out the whole formula again. Just our T star is going to change, so I'm going to do that in Desmos. Well, first I have to go to the T distribution to figure out what the T star is, and then I'm going to put that in Desmos. So back to 28.44. Okay, this is a little bigger, 2.047. Okay, so 2.09. Oh, actually, yeah, bigger degrees of freedom gives you a smaller T star. 2.047. Now I'm going to just change this number in here. And that changes the margin of error a little bit, right? So it changes it to 10.668 and 10.668. Okay, so what it does is it's giving you a little narrower interval. Negative 24.818 to negative 3.482 seconds. Okay, so I wrote that one down as well. Okay, so a little wider is more conservative, right? And a bigger p-value, let's just make a note of this. So we've got a little wider interval and larger p-value for the conservative or estimated degrees of freedom. Okay, pretty interesting. All right, and so I can see why if you didn't have technology readily available, you might just go with the estimated conservative degrees of freedom, right? Makes sense. Way, way easier than trying to do that formula. Okay, so I want to show you both of these on the theoretical calculator, and then we'll write our conclusion out. So yeah, this video is maybe a little bit longer. So back to our Staplet where we have our original data in, right? Since we already have it in here, and we did a simulation before, but we also have theoretical calculators at the bottom. So we have a 2-sample t-interval and a 2-sample t-test. And you can see other things that we're not going to do right now, but other things that are possible. So let's check our test first. Conservative, okay, so this is where if you put conservative yes, it will use just the smaller n minus 1. So some places call it estimated, some places call it conservative, and Staplet uses conservative. We are doing a two-tail test. So perform inference. So this is our t star, right? We got the 2.7151, and the p-value, yes, it's just different on the last digit. So we got our p-value right here, and it's just different on the last digit. Okay, if we do conservative degrees of freedom, it shows you that 19 is the estimate right there, estimated. If we put no, then our p-value changes and it calculates the degrees of freedom here. So this is how I'm getting the calculated degrees of freedom to show you, but I also want you to be able to do the problem without using the theoretical calculator and just use the theoretical calculator to check your work. So let's compare this one, same t star or t statistic and 0.0111. So yeah, again, it's probably just a rounding somewhere. Maybe they used a different value for these s's. So very slight difference, but very, very close. Okay, so please do use that to check your work, but be sure you know how to use the formulas as well. Now let's go to the 2-sample t-interval. And we started with the conservative, and we had 95% and 25.0578, negative 3.2423. So yeah, again, just 1 digit difference there. Okay, and now let's change it to 2844. Oh, all we have to do is say a conservative no, and you can see it right there. Also, maybe they use more digits on the degrees of freedom. That's another option that might make account for this last slight difference. Negative 28.818, negative 3.482. Yeah, same, just a difference in the 4th digit. Okay, pretty cool, huh? So that's a lot of stuff. Now let's go ahead and summarize all of this. So I'm gonna get the next page here. We've got a blank space on the next page. Continued. Okay. What does all this mean? So let's start with our hypothesis test, and then we'll talk about the confidence interval and whether they agree or not. Okay. So with a p-value of, and now it's like, which one do you use, right? I'll go ahead and use the conservative one, but I don't think it matters. We reject the null hypothesis. And so this is very similar to what we wrote out for when we did it with simulation, right? Same conclusion, essentially. There is evidence. We could compare a p-value to that one. My pages are all over the place. You can compare and see how they came out. Oh yeah, wasn't it 0.16? So yeah, same ballpark. There is evidence of a significant difference in wait time for a treat between kids who watch fast-paced cartoons versus educational shows. Aren't you curious about the coloring drawing group too? So I do have a link of the actual study, so you can take a look at that. Also, another thing is maybe they could use a bigger sample size and maybe they would get a nearly normal sample. So you might have been thinking of that option as well. Okay, so now let's interpret this confidence interval. So it's great to do both because it gives you the full picture, right? So now we can say with 95% confidence, four-year-olds who watch 9 minutes of a fast-paced cartoon have a, and now I want to say blank to blank, longer or shorter average wait time, right? And again, we got to figure out which set to use. This is when they're negative, remember we want to flip them and make them positive. But because it's negative, we know that the first group is shorter than the second one. So if it was positive, it'd be higher. If negative, it's shorter. So let's go ahead and write this out. Fast-paced cartoon have a 3 point, and now I'm going to cut it down to 3.2 because 3.2 for blah, blah, blah doesn't really help anybody. 3.2 to 25.1, rounding that off because it's 0.5. I'm just using the conservative one. Second, shorter. Right, because of the order we chose, the cartoon group was first. So that means the educational is longer than, yeah, educational is longer, so cartoon is shorter. So you could phrase it in a couple different ways. Fast-paced cartoon have a shorter wait time, shorter average wait time. I want to be sure I get the average in there for a treat than those same population, those who watch. I could repeat the 9 minutes if I wanted to, or just those who watch an educational program. Okay, great. So we've interpreted both. Now we want to talk about whether these agree or not, right? So how do we determine that? And if you want to take a moment and think of that yourself, you're welcome to do that. Just pause it. Our null is 0 seconds, right? So if the null is in the interval, then that sides with the null. That agrees with the null. And it's a two-tail, so we're just talking in or out. It doesn't. If it's a one-tail, we have to think, well, which way is the interval, right? If the null's not in it. So they're both negative, so 0 is not in there. And 0, this is fully below 0, right? So this supports rejecting the null. If it was fully above or fully below, this supports rejecting the null. So let's write that down. The two methods agree, meaning hypothesis test and confidence interval, because the null value of 0 is not in the confidence interval. For a two-tail test, and we rejected the null. Oops. A lot of writing on this video. So we need to state both of those, right? Because that's how they match. 0 was not in the interval, and we rejected the null. That's why they match. Hypothesis. Okay, very interesting. So we did a lot. I hope you're following it, and you'll get some practice, of course. And I'll see you in the next lesson.